So we've accomplished quite a bit. We now know the statistical properties of the decision statistics. For noncoherent communication that we're looking at, that receiver structure, there's quite a few of them. There's U0, there's U1, there's V0, there's V1, and for all four of those, we've now analyzed the cases where we assume that S0 was sent. So we know how all four of those things behave when S0 is sent, and we also know how all four of those values behave when S1 is sent. So we've gotten a lot done. What it boils down to is now we have a decision statistic vector that we'll call Z as usual. This vector is not two-dimensional. That's one of the kind of worst cases we looked at this semester, but it's four-dimensional. There are actually four dimensions, U0, V0, U1, and V1. Given this vector, and given some instance of it, and that's what we mean by this little z of capital Z. This is the general random variable, and when I actually observe a value, we'll call it little z. What we need to be able to do is we need to be able to decide, did you send me S0 of t, or did you send me S1 of t? So that's what we need to work on now, actually using this information that we've derived to come up with the optimal decision rule. We can show that the largest statistic decision, so right here, largest statistic, we abbreviate that LS in this section. It's optimal in a variety of senses. It's optimal in the minimax sense, meaning that it minimizes the maximum probability of error. It's optimal in a maximum likelihood sense, in terms of maximizing the likelihood of which was sent when you make your decision, and the equal probable Bayes sense, in terms of an average probability of error. So we're not going to do the derivation here. You can show that this is the thing to use. We're more interested in actually, taking this rule, what is the largest statistic rule, and understanding how to use it and the properties of it in terms of performance. So what is the largest statistic decision rule? So if you think back to the block diagram, once we got to U0 and U1 and V0 and V1, that isn't exactly what we were using in that block diagram. What we were actually doing was taking U0 and squaring it, taking V0 and squaring it, and calling this quantity R0 squared. Similarly, we were taking U1 and squaring it, U0, let's see, that should be a V1 right there. That's a little typo I need to fix. Yeah, so there's a little error here. This is right, U0 squared plus V0 squared. This should definitely say U1 squared plus V1 squared. I need to go back and fix that. But this quantity, U1 squared plus V1 squared, is what we called R1 squared. So really what we're doing on that block diagram is comparing R0 squared to R1 squared. What we're going to do is we're going to decide if R0 squared is bigger than R1 squared, then we're going to decide that 0 was sent. And if it's the other way around, if R1 squared is bigger than R0 squared, we decide that 1 was sent. So that's what we mean by the largest statistic decision. We're simply seeing who is largest, and that's a pretty easy thing to do. Given this vector z, take the two of the coordinates, square them, add them together. That's the number R0 squared. Take the other two coordinates, square them, add them together. That's the decision statistic R1 squared. And then just simply see which one is the largest. So that's why we call it the largest statistic decision. And this explains why we had the receiver structure that we initially had a few slides ago. We haven't proven that this is the best thing to do. You can go through that work, but this is why the receiver structure looks like it does. And while we actually aren't proving that here in this video, we are going to go ahead in the next video and go ahead and work through the math to show why this largest statistic rule actually is the case. So if you want the details, that happens in the next video.